Hello, everybody, and good evening. We are going to kick off the revision sessions for A2 Physics, and we're going to look at Unit 3.3 Kinetic Theory in this first session. Then and my colleague James Rydd from Cynfrig School in Bridgend will kick off a session 2 with nuclear decay, Unit 3.5, and then I'll come back for session 3 to do thermal physics, which is Unit 3.4, and then James Rydd will finish the recording sessions with nuclear energy, Unit 3.6. The live session will be a walkthrough by both of us of a past paper for Unit 3. So these are all predominantly Unit 3 revision topics this season. Okay, so we've got quite a lot to get through tonight to do kinetic theory of gases. And let's start with A, the equation of state and how we get that PV equals nRT. So we're looking at, to begin with, if we consider a gas and we look at keeping the volume constant, and volume constant, and then we change the pressure compared to the temperature, we see that the temperature increases as the pressure increases, but it doesn't pass through zero if we're going to do it in degrees centigrade. But if we then use pressure and convert the pressure temperature into Kelvin, then we get a directly proportional relationship where the pressure is proportional to the temperature. It's a straight line going through the origin, 0, 0, as long as that temperature is in Kelvin. So we can't use degrees C here, and this is known as the pressure law. Some of you might come across it in triple. Now, if we look at the case where for a gas, we keep the pressure constant, and this time we're going to be measuring the volume against temperature. So volume against temperature, and if the temperature is in degrees C, again we get a situation where as the temperature increases, the volume increases for a constant at a constant pressure, but we get proportionality only if we consider a temperature in Kelvin, all right, absolute scale. So we look straight line going through the origin, so we have volume is proportional to the temperature in Kelvin, and this is called Charles' law. Then let's have a look at if we kept the temperature constant. All right, so if we keep temperature constant, and this time we're looking at measuring the pressure and the volume. The pressure measured in pascals against the volume in meter cubed. We find that as the pressure increases, the volume will decrease. Okay, so we get this kind of like curve, and if we plot 1 over volume instead of volume, so pressure against 1 over volume, we find that it's a straight line going through the origin, i.e. the pressure is proportional to 1 over volume. We can say that the pressure is inversely proportional to volume because we're getting a straight line through the origin 0, 0. And this is called Boyle's law. Now, if we combine all of those together, we get the fact that pressure and volume, pressure is proportional to temperature, volume is proportional to temperature. So we can put those together and say pressure times volume is proportional to temperature. And we can use this for the number of, for example, PV, if we just rearrange that, divided by T is proportional to a constant. So all of those things can vary, PV and T. In fact, because it's proportional to a constant or even equal to a constant, in fact, this constant here is PV over T equals a constant. All right, and so we can say that it is equal to nR, where N is the number of moles and R is the ideal gas constant. Ideal gas constant. In fact, I don't need to, have this proportionality here. I can just say that PV over T equals a constant, which means if we change a set of conditions, then, and let's say we change all of PV and T, in fact, whatever that pressure and the associated volume and the associated temperature, then you change a set of conditions that will be equal to P2, V2 over T2, a second set of conditions, because each time they're equal to the same constant, provided that the mass of gas stays fixed and you haven't got any leakage or you haven't added any gas to the container. Okay, right. Okay, so let's move on. So what we can do though is we've got it in terms of moles there. So PV, rearrange this temperature here, and we get PV equals nRT like this. Okay, so we've got ourselves PV equals nRT. This is in terms of moles, okay, in terms of moles. But we might want to do it in terms of molecules. And in this case, we can use, instead of PV over T equals nR, we can use PV over T equals NK, where K is now Boltzmann's constant and N is the number of molecules. So that's a capital N. Little n tends to be the number of moles. And N divided by Na is equal to the number of moles. And in fact, K divided by Na will be the Boltzmann's constant. Just check. Yeah, so K is equal to the ideal gas constant divided by Na. Okay, all right, so let's move on. Okay. So you can see how we've gone from the number of moles to expressing it in terms of the number of molecules. And you can either use, it depends on which one you kind of like favor, working in terms of moles or in terms of number of molecules, or it depends on how the question is worded and how it's presented to you. Okay. So if we wanted to use it for, say, one molecule, then N equals 1, so PV over T equals K. And if we wanted to use it for 1 mole, it's PV over T equals R. Okay, let's move on then to the kinetic theory of gases, part B, kinetic theory of gases. And there's mainly 4 assumptions. And from those 4 assumptions, all else kind of like flows. So if you consider a gas in a container, those particles are moving. There's a random distribution of energy that those particles have. It consists of a large number of particles within that container. and they have random motion. So one of the assumptions straight off is that the volume of the particles that make up the gas is negligible compared to the volume of the container. Okay, the second one is that the intermolecular forces are negligible except during a collision. And it's probably worth pointing out here that because the volume is, assumed to be completely negligible, the particles don't collide with each other. They collide with the walls of the container, and that gives us the pressure. Okay, so when we're looking at collisions, it's the collisions between the particles and the wall. Okay, and the assumption is that the intermolecular forces are negligible, so you don't get this kind of like collapse of gases in on each other and attracting each other. There is no intermolecular forces between them, so that they are completely random and they're completely unaffected by each other, and they're completely spread around out of the whole container. And then so the force that they exert is on the wall during the collision, or during the walls of the container, on the walls of the container. Number 3, the time of collision is assumed to be negligible compared to the time between collisions. So what that is saying is that these particles are mainly kind of like moving at a steady speed towards the wall, and the time it hits with the wall is negligible compared to the time that they're traveling in between. Okay, so that leads nicely on to the fourth assumption, is that the particles move at a constant velocity. There is no forces acting on them, so they won't be accelerating. The particles are assumed to have negligible volume, so there's nothing in the way of them until they hit the wall. So constant velocity, they're moving with the same speed in the same direction. Okay, so particles move at a constant velocity between the collisions. Clearly, when they collide, the velocity is going to change. And we are assuming that the collisions themselves are completely elastic, so that the velocity that they have going into the collision with the wall is the same as the velocity coming out. It's just in a different direction. So what we need to do now is have a look at how this kind of like kinetic theory of gases relates to the macroscopic properties of, say, pressure, in this case pressure for part C. So we are going to look at the molecular movement and how it relates to pressure, the macroscopic. So we're looking at the microscopic, i.e. the kinetic theory of gases, and we're relating it to the macroscopic kind of like values of temperature, pressure, volume. Okay, so pressure. So pressure is given by force divided by area. Nice, easy one so far. So, and we're going to look at one molecule. So if we get our container of length L, of depth L, and at height L, and we have one particle in it, and that particle has mass m, and it's got speed c. It's traveling with a speed c. Okay, so for one molecule, the force is given by the rate of change of momentum. So that would be the final momentum, take away the initial momentum and divide it by the time. Okay, so we need to look at, so we know that when it hits the wall, say here, okay, it keeps going until it hits the wall, and then it kind of comes back on itself with minus C. So what we've got is we've got minus MC, we'll take the final minus MC. Okay, so that's taking this direction as negative. All right, divided by time equals minus 2mc over t. And that gives us our force. Now we need to pop that into the equation for pressure to relate it to pressure. Now, before I do that, I want to, okay, so the time here from speed equals distance. So speed equals distance divided by time. Okay, or let's have x divided by time, or L in this case, because it's going to go along the whole length of one side of the container. So speed is given L over T, which means if you rearrange it, the time is given by L over C, and we can substitute that into this here. So equals minus 2mc over L over C. But we can't have something divided by L divided by C. That comes up to the top and we get minus 2mc squared over L. Okay, right. Okay, now what we tend to do is, because we're looking at, eventually we'll be looking at all of the particles and all of the, so we look at root mean square speed, just mean square speed, not rooting it, just mean square speed. And we look at it like that because all of the particles have a completely random distribution of energy. So they could have different speeds. Their energy is proportional to the speed that they're traveling at. And so that's why we have to take a mean speed. And that mean speed is given by one speed squared plus another speed squared plus another speed squared, and so on and so on and so on. And we divide it by the number that we've got. So say we've got 3 particles, then we just divide it by 3. Right, okay, so let's do that. Okay, so that gives, I might come back to that in a little while. I divided by the number that you've got present in the sample. Okay, so moving on. Now we need to kind of like combine this a little bit. So let's say pressure is equal to force divided by area. Well, the area of the face that it's hitting, this area here, is given by L squared. So force is given by minus 2mc squared over L times by L squared. Now that area, the particle could hit one face, but it could equally hit another face up here, or it could hit another face here, depending on which direction it was going in. So that's why the 3 suddenly kind of like appears, because you've got 3 opposite faces for the particle. Okay, so therefore we've got three surface areas, and that's why the three kind of like comes in to the total surface area. So therefore total surface area is given by 3L squared. So I can put my 3 in there. But we know L times L squared is equal to volume. So minus 2 mc squared bar, i.e. mean square speed, over 3L squared. Now, what we need to consider is that this is the force of the molecule on the wall. So therefore, the force of the wall back on the molecule will be in the opposite direction. All right, if we've taken this direction as negative, then the force of the particle on the wall will be negative, but the force of the wall back, the force of the particle on the wall is negative, so the force of the wall back on the particle will be positive. Hence, the positive comes out there. Okay, so what have we got ourselves? So we have got so force mc squared over 3L cubed, and that is equal to volume. Okay, so that's 2 over 3 mean square speed, okay, over volume. So now I can combine it so that PV equals 2/3 mc squared over, that's it. All right. Okay. Some things are not quite right. So distance is 2L. The distance is 2L. Okay, so the distance that it's traveled is all the way there and all the way back. So the distance is 2 times by L here. All right, so that means that when we substitute the 2L here, it cancels out with the 2 at the top here. So in fact, what we've got ourselves is 1/3. Okay, so PV equals 1/3 m mean square speed. Okay, good. So for one, if we had just one molecule, this is just for one molecule. So if we wanted it for n molecules, all we have to do is times PV, okay, by 1/3 nm mean square speed, and that is for n molecules in the gas. But nm is the total mass of the gas. So that means that PV equals 1/3 m mean square speed, where that is the total mass of the gas. But you know that mass divided by volume is equal to density. So the total mass of the gas divided by the volume of the gas is given by density. So we get P equals 1/3 rho mean square speed. Okay, and we come up with the equation in part C. So you have to go back really, really carefully, all right, and remember, there's some key things here. Force is the rate of change of momentum. You've got to remember that the direction of the velocity changes. Then for time, you can do distance divided by speed, but you've got to remember the distance is twice the length that the particle travels. So in a sense, the particle is at one corner because it can have a choice of the three different faces. So the area that it bombards with is 3 times L squared, and that's where the 3 appears into the equation. And the 2 disappears because you've got the twice the length. And then it's kind of, substituting for pressure equals force divided by area, and then rearrange it and realize that density is the total mass of the gas divided by the volume. And then you get a really neat little equation. Okay, so let's move on from part B and C and go on to Avogadro's number. Now, I have touched on this. Avogadro's number is given by capital N. So this is part D now. Capital N A is Avogadro's number. Avogadro's number. And that is very, very specific. It's the number of 6.02 times 10 to the 23. That's the actual number. And it's the amount of either particles, atoms, nuclei that are in number of particles, in 1 mole of gas. In 1 mole of gas. Okay, so 1 mole of anything. It could be garden peas. If you've got 1 mole of garden peas, you will have 6.02 times 10 to the 23 peas. The definition of a mole comes about because we relate it to the molecular mass of carbon being 12, or the atomic mass of carbon being 12, but we relate it to the fact that in 12 grams of carbon 12, there is 1 mole, and i.e. there are 6.02 times 10 to the 23 particles. So 1 mole is defined as the number of particles, or we should be more specific, carbon, not just particles, but atoms, number of atoms of carbon 12 in 12 gram. Okay. All right, so let's have a look at the molecular mass. MR is the molecular mass. Now, this could be molecular mass, or molar mass. Depends, molar mass. Depends if it's an atom or a formula. For example, molar mass of air is 28 grams. So e.g. of air is 28.8 grams. So that tells me that in 28.8 grams, there is 1 mole. There is 6.02 times 10 to the 23 atoms or particles of air. We ought to say particles of air because it's a mixture of air. So if you had, let's have an example of a molecule this time. So if you've got sodium chloride, sodium chloride, and how much would there be in, say, 0.2 mole, then you know that the molar mass, the individual molar masses of sodium is 23 grams and chlorine is 35.45 grams. So we say that the molar mass of sodium chloride is add those two up together because the formula is just NaCl, so there's one of each. So 23 plus 35.45 grams gives you 58.45 grams. So that means that is the mass of 1 mole of sodium chloride, NaCl. So if that's the mass for 1 mole, just relate it logically. Don't try and be clever. Just that's for 1 mole. Therefore, 0.2 moles would be 58.45 times by 0.2, all in grams, to give you 0.2 mole. Right. Okay, so N is the number of moles, and that is given by the total mass divided by the molar mass. And the molar mass could be of a, of a compound or of a atom. So you've got total mass is given by the total number of particles times the mass of each particle. Little m tends to be the one particle, okay, divided by mr. Okay, and remember that mr is given in grams. So therefore we have to divide it by 1,000 to get the mass in kilograms. All right, so whenever you're given a molar mass, it's in grams. Divided by 1,000 to get it into kilograms. Okay, right, let's move on. And let's use now that PV equals nRT, and PV is also equal to a third nm mean square speed. And what we've got to do in part F here, in this part of the syllabus, is combine those two to get an equation. Yeah, to get a relationship between the internal energy of the gas and the temperature. So we need to combine them to show that the kinetic energy of a mole of gas, so you've got to somehow combine these two to get this equation, and they are expecting you to be able to do that. So that's what we will be doing now. Okay. And also this will be for 1 mole. Okay, so let's crack on. So relate the PV to each other. So on the one side, we've got nRT equals a third nm mean square speed. Okay, now, okay, mean square speed. So we have got, and I'll use mean square speed here. For example, if I've got 3 particles, all right, you've got the square of one, the square of another, square of the next particle, and divide it by 3. All right, you don't add them up, divide by 3, then square them. You have to square them individually. And that's why it's really, you square it and then you add the bar on top, because you're squaring each one of them, adding them up, and then divide by 3. Okay, so actually, while we're here, very commonly we use root mean square, which will just be the root of the mean squares. Okay, root mean square. And that's often symbolized by root mean square like that. Okay, all right. So essentially, it will be all that we have done there and just root it all. So all of that and like that. Okay, good. Right, so moving on. Right, so let's go back now to where we were. So RT equals NM. So if we have got it for, yeah, okay, right, yes, okay. So now we want to do it for 1 mole of gas. So for 1 mole of gas, we are going to, this will be the mass of 1 particle, little m. This will be the total number of particles, which means that m times m is the mass of gas. But if we have 1 mole, then we know that we've got Na. So for 1 mole, we've got Na is equal to the number of particles, because we know that 1 mole contains Avogadro's number Na. So Na times by m equals the mass of gas. Okay, so which means that we can kind of like simplify that equation and have RT equals a third um, M, that's the mass of the gas for 1 mole, mean square speed. Okay, so RT, now that looks very like a kinetic energy. So in terms of somewhere, I'm sure we can get ourselves a kinetic energy involved there, because the kinetic energy of the gas is given by a half m mean square speed. Okay, so what I'm going to do is, and that kinetic energy is represented by U, and that is the internal energy of a gas. Now, as you'll see in the next module, in session 3 module, when we do 3.4 thermal physics, I'll go into this in a little bit more detail to show you that the gases only have kinetic energy as their internal energy because of the assumption that there's no intermolecular forces, there's no potential energy in an ideal gas. In a real gas, a little bit different, but in an ideal gas, this is the case. So what I'm going to do is I'm going to put that kinetic energy into that equation by basically we've got, I'm going to a third, I'm going to take the third out, and I'm going to times that by 2 over 1, because I'm going to put the half in. Can you see that the 2 over 1 would cancel out with the 1 over half? But it kind of like is really convenient for us because I don't want to cancel them, because I want to keep the kinetic energy as kinetic energy half mv squared. So what I can do now is just combine that 2 over 3 times by the kinetic energy of the gas. So all of a sudden I've got this kind of relationship between the kinetic energy and the temperature, and it's showing us that the kinetic energy of the gas is directly proportional to the temperature, as long as that temperature is in Kelvin, which will lead us on to nicely absolute zero. Okay, and I might as well, so if there is no energy, there won't be any temperature. So at 0 Kelvin, it's the minimum possible energy that gas can have. And assuming that the potential energy is already 0, the kinetic energy will be 0. So let's rearrange this. So the kinetic energy of the gas is given by 3 over 2 RT, and that is given by U. So we've got 3 over 2 RT equals U. Now that is looking in terms of moles. Let's just check. Just want to check. So that's for the gas. So we can do it in terms of molecules, or we can look at it in terms of, let's go back to this one here, RT equals 2/3 Na, Avogadro's number, times by a half mc squared, like that. This would be the kinetic energy of one molecule. And this is the total number of particles in 1 mole of gas. So we can look at it like that. So kinetic energy of one molecule will be 3 over 2 RT divided by Na equals the kinetic energy of one molecule, not the whole gas. So R over Na, as we saw earlier, is equal to Boltzmann's constant K. So 3 over 2 kT equals the kinetic energy of one molecule. Whereas when we were looking at it earlier with this one here, we use that for moles. Okay, so that is for 1 mole of gas, whereas this one, 3 over 2 kT equals U, is for 1 molecule of gas, like that. Okay, but essentially what that says is that temperature is proportional to the internal energy. Okay, so and the mean kinetic energy is proportional to that temperature, i.e., the temperature is directly proportional to the mean square speed. So a macroscopic quantity, temperature, that we can measure with a thermometer is directly proportional to something that is happening on a microscopic level. Okay, so let's have a look back to where we have come from. I just want to check that I have done everything. Okay, and I come all the way back up to the top and just go through each of the parts that we've done. So we've looked at PV equals nRT. We've looked at PV equals nKT. So this one would be for the mole, and this would be for a molecules. Okay, in terms of moles or in molecules. We've looked at the 4 assumptions of kinetic theory of gases, and we've kind of extended them a little bit also because WJC will accept a little bit more in their mark schemes. We've had a look at how we get this equation, pressure, and how it relates to the density and the mean square speed. And then we went on to looking at the definition of the Avogadro's constant and the mole. And then we looked at the molar mass and how it's related to the relative molecular mass to give us the number of moles. And remembering that all of these masses are in grams, and we can convert them into kilograms. And then finally, that quite a tricky kind of like relationship between PV equals a third nm mean square speed with PV equals nRT, and relating them together. You will be expected to be able to do this in an exam question, relate them together to get out 3/2 RT or 3/2 KT. So 3/2 RT is for 1 mole and 3/2 KT is for 1 molecule, where K is Boltzmann's constant and R is the ideal gas constant. The ideal gas constant is given to you. I can't remember where the Boltzmann's constant is, but in order to work it out, all you have to do is R divided by Avogadro's number. So K equals R divided by Avogadro's number. Okay, so that is a resume of kinetic theory of gases. We'll see how that relates into a Unit 3 paper when we run through in the live session, a Unit 3 paper, and there'll be a question on the kinetic theory of gases. So remember, next week will be session 2. That will be held by Mr. James Ridd, and he will be doing nuclear decay. All right. Okay. Good night. And I hope that you've got something from this session.